Recording's rolling. It's Tuesday, November 18th. So we're doing this page today. Give you guys a couple pointers on this. Right, so these questions right here. This is printed on the opposite side of the one that you guys did already. Right, so it's just more momentum puzzles, but it's from Honors Textbook. Yesterday, I gave you guys a momentum take-home quiz. So it's due after the break, but I gave it to you guys plenty early this time so that you could turn it in before the break, and then it would be off your mind, so you could, if you want to turn it in before the weekend, right, before Thanksgiving break. Right, but here's our focus today, are these puzzles. Right, so straight out of an honors book. Right, so most of these are straightforward momentum questions. So here, I'll give you guys a review of momentum. Right, you guys know that momentum is mass times velocity. This is a vector value, and it's conserved in collisions. Or whenever you have a closed system, it's always conserved. Okay? So here's general conservation of momentum. Right? So if you add up all the momentum bits before and after the equation, they have to equate. Right? So you guys know that. Okay? Now, if you ever see a question where it says two objects couple together or stick together, then there's a modified version of this. So it starts out the same. You just add the mass times velocity that's together. Right? But then they combine and make one giant mass with some common final velocity. So you can get something like that. Okay? All right, those are some of the main questions. If you see a question about impulse, that could be force times time, results in a momentum change, mass times velocity. And there are a couple questions on here that have to do with a lab that we haven't done yet that I want to do with you guys next couple days called coefficient of restitution. So this quantifies how bouncy is any particular collision. Anywhere from on a spectrum from perfectly inelastic to perfectly elastic. And a lot of times, realistically, it'll be somewhere in the middle, like two tennis balls going. Right? So you say, what's the difference in velocities post collision? What's the difference in velocities pre collision? And divide it, and then just take the positive value, the opposite value. Okay. Now, if you bounce a ball off a floor, there's a special version of this. So you're bouncing a ball off the entire Earth. We'll consider the Earth not moving. So the difference in velocities would just be the velocity of the ball. Okay. And based on a height drop, do you guys remember from conservation of energy, the crash speed could be square root 2gh. Okay. You can also do rebound speed for 2gh based on the rebound height. Okay. So you take that ratio, works out like this. Okay. So this is a lab I want to do with you guys pretty soon, but not quite today. Okay. So we're just be solving some of these momentum puzzles today. Okay. All right. So here, what I'm going to do is just read these with you guys so you guys can think about these. And there's only, I think, just one or two that I actually want to solve with you guys. Right. But you guys can help each other out, and then if you don't finish these all today, then that's where I'll keep track of about where you guys are. Might give you guys more time later in the week. And so we got the driver has a 244 kilogram snowmobile. Now, of course, everybody's paper is different, so you probably don't have that mass specifically, which results in a force that speeds up the automobile or the snowmobile from this speed to this speed over this time interval. Ooh, do you guys see a change in velocity over a change in time? Right, so I'm already thinking something like this. Something like this. Okay. So guys, they gave you a change in velocity, they gave you a change in time, and they told you the mass that's being accelerated. Could you guys find the average net force on it? Okay. That's exactly what they're asking for. Boom. Right, that's how you do that one. Okay. All right, next one. We got a softball pitched at this speed. The ball moves in opposite direction, which is underlined. Right, at this speed after it's hit by the bat. The contact time is this many milliseconds. Guys, that prefix milli, that's 1 over a what? 1,000. Yeah, 1 over 1,000. So can you take the number in the box and just divide by 1,000? And that would represent how many seconds? Per second. Bam, so fast. Which is the average force? Well, that sounds like this too. Okay. But here, guys, there's a little twist here. So here's the mass of the softball. So you can plug that in. And I gave you the time interval. You just divide the numbers milliseconds by 1,000 to get the number of seconds. Okay. The question is something about average net force. Okay. Now, change in velocity. Right, here's where I'll give you guys a little hint. If there's a ball being hit by a bat, I'll change the numbers a little bit. Let's say the ball comes in at 20 meters per second to the left, and it's hit back, bam, 30 meters per second to the right. Okay. Guys, you can tell me for this scenario, what is the change in velocity? And don't say 10. 50. Aha! It is 50 meters per second. Okay? Because the ball changed direction. And velocity and momentum are both vector values. So it matters if it's going left or right. It matters. Okay? So the way to get that systematically is say, well, we ended up going 30 meters per second minus negative 20 meters per second, because you have to consider change in direction could be like a negative value. And that leads back to paper towels. Okay, so you guys good with that? Okay, so you can feed everything into here.
So that again, I didn't get that.
Oh, okay. All right, guys. If the ball is pitched at some speed to the left and it's hit back towards the right, okay, anyone want to find the change in velocity? Okay. Well, if you take the final velocity minus the initial velocity, but don't forget that the fact that it changed direction, there's also a sign change. So you're subtracting a negative value. 30 minus negative 20 isn't that the same thing as 30 plus 20, which is 50? Yeah.
So if they were traveling in the same direction, it would still be minus, but the 20 would be positive.
Yeah, like if the ball was going towards the left and you hit it with the bat and send it even further to the left,
Yeah.
you would just subtract
So
two
it,
positive numbers.
so it would only be plus 10 in that scenario.
Yeah. In that case, it would be. Yeah.
Okay.
If it was going to the left at 20, you hit it down, so it's going even faster to the left. Yeah, the difference might be like 10. Right. Okay. Yeah, that'd be good. All right. All right, two freight cars, each with this mass, so they have identical masses, collide and stick together. One was initially moving at some speed, and the other was at rest. All right. Yeah, I think you guys had a lab a while back. You guys remember those collision carts? Collision carts, right?
Yeah.
In the first version, I taped on some bar magnets so they would stick together. They would couple together. Okay? Well, that's this right here. Except even simpler because one of these carts starts at rest, so it adds no momentum to the system itself. Right? All the momentum comes from initially the cart that's in motion, right? And they stick together. They combine mass. Okay, you guys saw that?
What
yeah.
does the momentum questions do?
End of the week. End of the week. Yeah. Oh, we got okay, hockey puck. Okay, so I gave you a massive hockey puck. It's moving at some speed. It's caught by a goalie who's at rest. What speed does the goalie slide on the ice? Okay. Well, ice in physics is considered to be frictionless. Right? So once you catch the puck, you're going to start sliding backwards. Right? Okay, so that's also this. It's the same poster. Right? So the goalie starts at rest. So this term goes away. Here's mass of the puck, velocity of the puck. Right? And then when the goalie catches the puck, don't they make one giant mass of goalie plus puck? Right? And they slide off at how fast? You're solving for this right here. Right? So it's the same equation as the previous question. Right? A bullet. I told you how many grams is the bullet. Moving at this speed strikes so many kilograms bag of flour that's on ice at rest. Right? The bullet passes through and exits at some speed. How fast is the bag moving? Okay, guys, here's a little detail that's important. Otherwise, you'll miss this with the calculator. Okay, so look at those masses. The mass of the bullet, the mass of the bag of flour. Are those in the same unit?
No.
They are not. The mass, the bullet's in grams and flour's in kilograms. Do you have to make those the same unit?
Yes.
So, yeah. Whenever you go plug in values in the calculator, you can either divide the mass of the bullet by 1,000, or I guess if you wanted to, you could turn the flour into grams. You would still get the correct answer. Right? But you got to make sure it's consistent. Okay. Now, this is more like a general conservation of momentum. Okay. Because post collision, the bullet does continue through the bag of flour. It's just going slower. Right? And so it transfers some of its momentum to the bag of flour. Right? So it's more of a general case for that one. Right? A little trickier, but I'm going to see if you guys can solve it either by yourselves or with your friends. And of course, I'll walk around and you guys out too. We got number 18. A ball is traveling at the speed, collides head on with a different ball, different mass, going the opposite direction at this speed. Okay. And then they bounce off each other, boing, right? And I gave you just enough information. Right? Find the speed of the other ball. Right? So that's just straight up general conservation. In fact, the pictures actually match this time. Right? So I told you the mass of two different balls. Right? They're headed towards each other. Because the fact that they're headed towards each other, if one velocity is positive, the other must be what? Negative. Okay? And if you miss that detail, you're going to get it wrong. Of course, there's multiple choice, so you're going to know right away if you made a mistake or not. Right? Yeah, headed towards each other, the velocities have to be opposite sign. Right? And they bounce off each other, but boing, and then, well, I bet you guys can. If I gave you all these variables except for this VBF, could you solve for VBF? How's that? Okay, number 20. A thread holds a 4 kilogram cart and a 2 kilogram cart together. After the thread is burned, a compressed spring pushes the carts apart. Okay. What's the velocity of one cart if I tell you the velocity of another cart? Here, I will draw this one out for you guys. So there's these two carts with different masses. So, well, I'll call it mass A and mass B. which I gave you numbers for, but my numbers are different than your numbers. Okay, there's this compressed spring that you guys see this compressed spring wants to push them apart. Okay, maybe they're on little wheels on a low friction track. Okay. But there was also this thread holding together. There's huge tension in this thread. What we're gonna do is cut this thread right here, our little scissors, cut that thread, and then the spring is gonna uncompress. It's gonna push these two apart. Okay. You know what this reminds me a lot of? Actually, is do you guys remember that magic school bus question where the pitcher threw the ball and they were on a frictionless baseball field and then she was sliding back towards second base the other way? You guys remember that? Okay. And if you know the mass of the ball and her mass and the velocity of the ball towards the plate, you can calculate her velocity back towards second base. You guys remember that? Okay. So there's zero momentum in the system. Momentum is conserved. That means that MV of the ball to the left is MV of the skater to the right or the pitcher to the right. Right. Or in this case, we got two cards, but it's mathematically identical. You guys see that? It's the same thing as this. It's this one right here. Right? Yeah, so you guys know all these posters I'm showing you guys. They're all painted over on that wall, or you might have the thumbnail notes on a lot of these. Okay. All right. Now this next one is I actually do want to do with you guys. Number 22. We got a car moving north. So there's a massive velocity going north, and then it collides with this other car, massive velocity, going west. The two cars stick together. What's the speed and direction that they move after the collision? Okay. So I've really been focusing on one-dimensional collisions with you guys. This is a two-dimensional collision. So let's do this one together, number 22. And if you're lucky, maybe you have the same numbers that I do. Okay. Right, so let's get a Cartesian system going. Cartesian system. I guess I'll call north upwards, and then east to the right, and west to the left. Right. So that could be traditional compass rose, right? Okay. And one car is moving north, so if we're up in a helicopter looking down, I'll call this guy 950 kilograms, so that's the number straight off my paper. And he's going at 18 meters per second, heading straight towards the center section. Then there's another car. So this car right here has mass of 1650 kilograms going straight west at 15 meters per second. These two cars are gonna bam collide where I put the origin of my axis was on for. Okay. Okay. Now guys, if one's going north, one's going west, and they collide, bam, do you think they're gonna kind of overall drift northwest? Do you guys think? Okay. Now, which way northwest? Is it more north or more west? Do you guys think that would depend on their masses and their velocities? Right. So it looks like my north car has less mass, like almost half mass, but he's going a little faster. And the westward moving car, well, he's like almost double the mass. He's going a little slower. So I think this east-west one is overall has more momentum. So I think it's going to go more west than north. At least that's true for my paper. It may not be true for yours, right? So I think when they couple together, I think they're going to move off kind of this direction. Something kind of like this.
Mr. Griffin,
Yeah.
what if the smaller car moves almost double the speed of the big car? Like mine says an
Okay.
100 kilogram part moving at 29, collides with the 1100 kilogram part moving 15.
Okay. Yeah. In that case, I think the smaller car would have more momentum. That's possible too. Yeah. Right. If the smaller car is only a little bit smaller and it's moving like double the speed, you could have more momentum. Okay. Yeah. So whichever has more momentum, you guys know momentum is just mass times velocity. Right. So you can compare it that way. Okay. So the two questions are what's their combined speed and also direction. Isn't that what velocity is? Speed and direction? Okay. So we're also going to solve this angle. So we need to find both those things. Okay. And there's easy ways to get this wrong if you just go straight through velocity, but you have to consider momentum because they're going to collide and so on. Right? So what's conserved is momentum. What's conserved is momentum. Okay. So it's going overall north and also west. Same time. And I'm going to dash these components. Then we'll make sense of this. Right. So here I'm going to switch to pink ink. So everything in black ink is kind of what's set up. Right. And then right here. Alright, let's get some products here. So you guys know that momentum is mass times velocity. Let's figure out what's the northward momentum. Well, that'll be 950 kilograms times 18 meters per second. I'm looking at 17,100. So I'll say P north, so that's momentum in the north direction, is 17,100 kilogram meter per second. Okay, it's all from my northward moving car. Okay? Okay, you guys following also with your paper and your numbers? Okay. Now, what about this westward moving car? Well, it has this mass, 1650 kilograms, and it's going 15 meters per second. I'll just call west the positive direction. No, did all my numbers will be positive. Okay. So that comes out P west is so momentum west is 24,750, also kilogram meter per second. Okay, so say units. Okay. So the two-car system has overall this much northern momentum and this much western momentum. Okay. Okay, you guys able to follow that? Okay. Momentum is mass times velocity. This mass velocity results in this momentum. This mass velocity results in this momentum. Right? Okay. Okay. Right, now what? Ooh. Guys, what shape is this called right here? A right triangle. Hey, if you know the two legs of a right triangle, how do you get that hypotenuse?
A squared plus B or Pythagorean down.
Yeah, Pythagorean theorem. A squared plus b squared c squared. So that's it. Here, pull out some more paper. So I'll say P total squared equals P north squared plus P west squared. Right, will that be true? Because two dimensions, Pythagorean theorem. Okay. So P total is the square root of these values squared. I'll just go ahead and pop them in right now. So 17,100 kilogram meter per second being squared plus 24,750 kilogram meter per second being squared. Okay. So we take the square root of the sum of the squares. That'll tell me the total value of the momentum off on that angle. So P total is calculator time. 100 squared plus 24,750 squared. Okay. I'm getting this number right here. A kilogram meter per second. Right. Okay. That's the total momentum off on this northwest type angle. Okay. It's just Pythagorean theorem. Okay. Are you guys good with Pythagorean theorem? Good with Pythagorean?
Yes.
Everybody's good. Who's good? Okay. Okay. Now we're getting pretty close. Okay. But the target question, well, the first question, there's two questions. The first question is, how fast? Like, what's the velocity? Yes, if you know the total momentum of the two cars, how do you get the velocity of the two cars? The speed.
Mass times acceleration, right? Or is that's force? I don't know.
Here. Okay, it's right here. If you know P,
You can divide by the total.
and you know M, yeah, just divide by M. And in this case, the combined mass, because there are two cars crumpled together. So we're going to divide by the combined mass, and that will tell us the combined velocity. Because they're stuck together. Right? You guys get that? Okay, so let's do that. So V, well, I'll say the magnitude to be like the speed, okay, would be the momentum divided by the combined mass. And it'll say mass A plus mass B cars. Okay. So I'm taking my 30,083 kilogram meter per second, or whatever your number is on your paper, divided by the sum of the masses of the cars. So my cars were
1650.
yeah, right, 950, 1650. You guys remember that? Okay. 950 kilograms, 1650 kilograms. Right. So total momentum divided by total mass should give me the total velocity. Okay. So 30,083 divided by 950 and 1650. Okay. All right, I'm getting 11.57. I'll call it 11.6 meters per second. Okay. Which is exactly one of my answer choices. That's right there. How about you guys? Are you guys able to follow your numbers on your paper? Did you get an answer? Okay. Now that's actually the speed. I've been saying velocity, but really that's a speed. To make it a true velocity, you also need the direction. So, how can I find the direction, which I've labeled theta? Okay. You guys see it's relative to the north-south line? That's a convention that's called bearing. If you want to measure relative to the north-south line, so many degrees west of north. You guys it? Right. Who remembers? We did this a long time ago in this class. Who remembers how to solve for theta? Yeah, it's something to do with right triangle geometry, right?
There's something close.
Okay. Yeah, there's sine, cosine, and tangent. But if you want to extract the angle, you have to apply what? Inverse. Inverse. Right. Now, since I have the two legs here already written, then I'll take an inverse what? Tan. Yeah, inverse tan. So guys gotta say theta equals inverse tan. And then it'd be opposite over adjacent. So for me, that's 24,750 divided by 17,100. And then, well, I'll leave it. It's kilogram meter per second, kilogram meter per second. So anyway, right. That'll tell me how many degrees west of north. And so I'll hit inverse tan. Right, so hit second tan, I'll bring up inverse tan. Okay. 24,750 over 17,100. Okay. I'm looking at 55 degrees, and that's west of north. Okay. Is that an answer choice on my paper? Oh, even better, because my calculator actually says 55.359 something, right? And the answer on my paper says 55.4 degrees. Yeah, so it's there. And that's west of north. Okay. All right, that's it. All right, so yeah, we brought in some trigonometry, put momentum into two dimensions. All right, you guys good with part collision? All right, of course, I'll post this video, so if you need to go back and review that again. Okay. But here, we're going here. Next one, 66. Hey, look, it's a force versus time graph. We got a baseball acted on by some force or some time. No, it is a variable force. Looks like the force increases, decreases. Okay. What's the change in velocity of the baseball? So that sounds like a job for impulse. Oh, actually, my graph looks the same too. See that triangle shape, that classic triangle shape? Because the force builds up and dissipates. Okay. So, guys, what's the area of a triangle? 1/2 base height, right? And the base here could be, well, it looks like 2 seconds, and the height might be like 2 newtons. Okay. So that could give you an impulse. Okay. So the impulse could be F delta T. Right? Isn't the area of that triangle that takes the place of all of those, doesn't it? Right? If only you knew the mass of the baseball, you could divide that over and get the change of velocity. Oh, that's the whole thing. You guys do it? Impulse right here. So impulse. Next one. How bouncy something is, coefficient of restitution. And I gave you both perspectives shoved into a single line right there. So if I'm with two posters. Okay. So one perspective on coefficient of restitution is the ratio of post-collision compared to pre-collision difference in velocities. Right? And another perspective is the special case where you bounce a ball off the floor. And it turns out if you do the same thing and it ends up being the square root of the ratio of the heights rebound compared to drop height. It ends up being the same thing. Okay. So I gave that all right here. It's all right there. Right, there's a couple formulas all shoved in one line there. Okay. So determine the post-collision velocity. Object A goes with object B. If looks like question number A, I gave you the coefficient of restitution, and I'm asking for the final velocity of object A. Okay. So that's like this. If you know this number, and you know both of these numbers and this number, could you solve for this number? Okay, yeah. So it's just a little different algebra application. I think you guys can figure that out. Question B, determine the rebound height of a ball that was dropped from this height where with this coefficient of restitution. Okay, so this is a bounce ball off the floor scenario. Okay, and that's this right here. So for question B, I gave you the drop height, that's capital H. I also gave you coefficient of restitution. So I gave you how bouncy it is collision. Can you solve for the rebound height? Next yet? Let's see that. All right. Question C. Oh, perfectly elastic. All right, so if I'm like perfectly elastic. Okay. So if something's perfectly elastic. Okay. Have this in mind. Newton's creative law. Yeah, see how bouncy that is? Boing, 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 boing. That's probably as close to perfectly elastic as you can get. Okay. And in physics terms, what's conserved is both momentum and kinetic energy. And then if you take the system of equations and solve it, it's always the Goldilocks. Okay. Did I tell you guys? I think I may have told you, but just make sure I got my bases covered. If you take physics in college, then it's really hard to find this equation either on the internet or in any physics textbook. Right? So if you hold on to this, then when you see a perfectly elastic question. This will save you a lot of paper and a lot of time. Okay, so hold on to your notes and high stuff. Okay? But that's what we got going on here in question C. And I gave you the solution to the system of equations. And the question is determine the post-collision velocity of object A if it's a perfectly elastic collision. And I gave you the initial velocities of the objects going into the collision and the masses, right? But it's set up to solve. So there's no algebra involved in this at all. It's all straight arithmetic because you just plug these numbers in. And the target question, what's the post-collision velocity of A? It's set up to solve that, right? Now, the very last question, question D, involves angular momentum, which we have not done yet, which is a pretty cool question. Have you guys ever seen ice skater, like figure skaters? They go into spin, they pull their hands in, they spin faster. Right? That's called angular momentum. So we'll eventually talk about that. Maybe December, but probably more like January. Right? So cross out D. Right? So we're not going to do D. Oh, it's not too bad as well. Right? All right. So there you go. That's exactly what I wanted to tell you guys. And you guys got the rest of the class to work on that. We got a solid 20 minutes. I'm going to check on you guys and see where you are. Right. As soon as you finish, you can turn it in. If you don't finish today, then that's all right. You can turn it in before the break.